Next up is Gawen. So Gawen is Professor of Applied Geology concerned with mineral resources and how we can provide these more sustainably, looking at how we might reprocess old mining wastes for metals to reduce the need for new mines. Today, Gawen is going to talk to us about mine wastes, a diversity of metalliferous anthropogenic deposits. So over to you, Gawen.
Well, talk about today is just an overview put together with my PhD students on work we're doing. And we're going to cover waste rock, we're going to cover tailings, we're going to cover metallurgical slag. And the importance of these things is there's vast amounts of this waste material produced every year, big numbers, 100 billion tons. And some of this material may contain valuable metals. That's something that we're interested in perhaps extracting so we can avoid new mining, but also it's an environmental contaminant if we don't do something about it. So just to explain those terms, so we're mining to get some metals, and we might be an open pit or underground, but everything we mine isn't the ore that we actually want, that's economic to get the metal out of. There's a lot of rock that we need to tunnel through or dig out before that, and that is waste rock. And then we get our ore, which is what is economically useful. That in general will be crushed down to a fine sand or silt, and then we'll do some sort of concentration process on it, maybe gravity or flotation, to get out our metal bearing materials into a concentrate. What is left over from that in large volumes is this finely ground waste rock with only minimal metals left, and that is your tailings. And then our concentrate, in this case for copper, would be smelted. And a byproduct of smelting, of course, is our silicate material that is not our metal, and that becomes metallurgical slag. And the figure at the bottom really shows the fact that the metal that we actually end up with is a very small proportion of the total material that's actually mined. And we've got some figures for it here on the right. So just that first column, waste to ore, it shows that when you're mining copper, the waste rock is about 1.86 or 2 times what you're actually, the ore that you get. Gold is even bigger, lithium about 5 times. And then metals are present in different concentrations that are economic. It varies between commodities, and that feeds into the overall rock metal ratio that we can see there on the right. So copper has a number of 513. That means if we want 1 ton of copper, we need to mine 500 tons of material. Okay, gold, 3 million. Okay, so if we want a gram of gold, we're mining 3 million grams or 3 tons. So these give us an estimate of the sort of amounts of different waste products that we'll get, and they give us an impression of the carbon footprint and the environmental impact of this mining. So first of all, waste rock. Here we are, it's stacked up in piles. This is Rio Tinto in Spain, and often it's sub-economic material, so it will contain some mineralization. So here we've got sulfide ore, it's oxidizing in the environment, that's giving us these ochreous colors, and the other product, of course, is sulfuric acid that goes down into the rivers. We have a very acid, iron-rich water there, and that gives us the name Rio Tinto. Closer to home in Cornwall, there's been extensive historical mining, as we know, and that gives us the landscape and the heritage landscape that we know and love. But again, it is an environmental contaminant in places. So here's an example that we're working on and examining, and you can see it's very variable. So if I was to describe it as a sedimentologist, which I'm not, layered of some sort, highly angular, class-supported breccia. We've got a mixture of vein material. We've got the host rock material as well. Big variation in grain size. And in the middle picture, you can see it's often cemented by iron oxyhydroxides. Some of those samples of vein material will be full of sulfides still. So on the right, you can see a rich sample of zinc sulfide. sphalerite, others will be completely barren. So overall, that's very hard volume of rock to characterize. Say we wanted to remine it, how would we actually characterize its composition, given it's so variable? And one of the things that Revan is doing here in Cornwall is looking at using geophysics to get bulk properties across these mine dumps to see if we can distinguish different areas. So this is electrical resistivity tomography. It's just looking at the resistance using electrodes. And what we can see is we can certainly define the base of the waste dumps very clearly above the soil, that is the bottom blue area. And even within those waste dumps, we can see different areas that relate to whether they've been cemented or are unconsolidated. So this is looking very promising in terms of at least characterizing our material before detailed sampling. And then our second product, tailings. So this finely ground slurry is typically pumped into dam structures and stored there. So this is the modern one from a mine that we're working with in the Philippines. And there are vast numbers of these deposits around the world. Estimate 280 billion tons of material. And perhaps there's vast amounts of metal contained in them that we could perhaps recover. Now, that's a modern deposit, but we're actually more interested in the historical deposit that was put down in the 1970s, the first tailing storage facility here. And at the time, the processing was less good. So there's still quite a lot of residual metal in this material, about the same as what they're currently mining, actually. So we've been working on this in a big joint UK-Philippines project, looking at how we might remediate this material and we might extract the copper. And in doing that, one of the things we did, we did some trenching just to look at the material, and we can see different layers. For example, at the top, we've got a sort of reworked sandy layer that's been redeposited by the streams running over the area. And then further down, we go into this sandy clay laminated material. But if we look closely, there are potential sedimentary structures. These look like flame structures to me, but again, I'm not a sedimentologist. Is this evidence of dewatering after they've been deposited, perhaps? And in the back, and I've zoomed in at the front here, we can see channel scours, of course, the material cutting through preformed layers there. And there's something interesting there on the left as well. Let's zoom in on that. Now, that looks to me like an asymmetric fold. Okay, so how on earth did that form in this environment? We don't really know. Possibly dewatering? Is it slumping? Is it seismically induced? We really don't know. So I'd love to know what people think about that. And then another area here, we've got what I would call the junk horizon here. So all sorts of rubbish is also put into these tailings facilities. So we've got waste scrap metal and tires and things over the unweathered tailings material. And perhaps on the right, you can see, again, big heterogeneity, cross-bedding structures indicating current flow. And that material has been there for 50, 60 years on the surface, so it is weathering, it's oxidizing in the environment. So our original sulfide grains here are surrounded by iron oxyhydroxide rims. And we think that's actually where a lot of the leachable copper that we're able to get out is actually hosted. And then finally, slags. These are the silicate material that's separated from the metal sulfide bearing material in a smelter. And this is taken from the smelter and tipped out in huge piles and left to solidify very rapidly. We can see that in the background on the right. We have this barren area of these black slag dumps. And again, we're working on these closer to home. So we have occurrences in Cornwall that we're looking at. We can see it's not a sediment. This is a volcanic rock. and Alex is working on these. We have a cross section here on the right, and we can see these little rounded blebs of material. These are shiny and bright, and when we look at them under the microscope, we can see bottom left that actually we have bright round globules of copper tin alloy. We have copper sulfide in there, all of which we could potentially recover, along with various silicate minerals, so skeletal, phthalite, and magnetite as well. And even these materials are weathering. So on the right here, we see chloride in our sample, and that's because it's oxidizing in the beach environment and forming copper chlorides. So just to finish off, what we're thinking about and trying to flesh out is understanding where are the best opportunities perhaps for reworking these materials. And in general, there's going to be a change with time. So we go from very high metal concentrations in old workings to much lower nowadays, but the mass of that material grows through time. And that's it. Thank you very much. I hope it was not a waste of your time.